Kumar from Wisman Institute of Science, and can you hear us?
Yes, can you hear me and see my slides?
Yes, we can hear you, and yeah, we see your slides now. So please feel free to go ahead. Thank you.
Yeah, thank you. So hello everyone, and so my name is Pravir, and I am a postdoc at Wisman. And today I'll be presenting results from our monitoring campaigns of one of the repeating FRB source 2018 301A. And this work has been done in close collaboration with Ray Lu, Danny Price, Ryan Shannon, Adam Deller, and several other people. So as the sample size of repeating FRBs has grown, there is an increasing diversity of phenomenology emerged. In some of the repeating FRBs we see periodic modulation, while in others we haven't seen it yet. Some of the repeating FRBs are associated with luminous persistent radio sources, while others are not. And there is a wide range of burst rate or burst activity rates in repeating FRBs, with some of the sources are very prolific repeaters, while others do not emit burst as much. There is also evidence of distinction between the repeating bursts and the apparently non-repeating bursts in terms of pulse morphology, with the repeating sources having wider temporal widths and narrower spectral extents. The polarization properties of repeating FRBs have also become quite diverse from recent observations. Earlier, while it was thought that repeating FRBs have distinct polarization features such as high linear polarization, no circular polarization, and a non-varying PA, which all turn out to be not correct. In one of the repeating FRB source 1905-20B, there is also significant Faraday RM evolution and evidence of RM sign reversals. So it turns out that repeating FRBs are fantastic probes of the magnetoionic environment of the FRB progenitor, and a long-term wideband polarization study is the way to go. So the source we are focusing in this study is 18031A. It was originally discovered at Parkes with a dispersion measure of 522 per centimeter cube. There were hints of circular polarization in the original detection, and the Faraday RM was measured to be minus 3000 radian per meter square. Although due to calibration issues, there were some ambiguities in the results, and these were not complete. Subsequently, many repeat bursts were detected from this source with FAST in 2019, and those bursts showed a diversity in the pulse structures, including the sap trombone effect. The average RM that was measured for those bursts were around 542 radian per meter square, and all the bursts had high linear polarization or almost no circular polarization. For the first time, there are very significant variations in polarization angles were observed in the source, which implicated magnetospheric emission. Later on, the source was localized to a star-forming galaxy at a redshift of 0.33. And in the VLA observations, there were no PRS found to be associated with this source. So we monitor the source using the Parkes radio telescope and using the ultra-wideband low receiver, which provides a continuous coverage from 700 MHz to 4 GHz. And a wideband observation is critical in order to truly characterize the spectral shape of the FRB emission, as is evident from this diagram, where I have compared the bandwidth of UWL with all the contemporary radio telescopes in the background of a single pulse from a trap pulsar. But with this wide bandwidth of data, the wide bandwidth, the data rate is quite huge. And in order to sensitive to band limited bursts, we employed a tiered subband searching strategy, where we divided the data into subbands of size ranging from 3 GHz to as low as 64 MHz. And we conducted the FRB search using the standard methods using tools like handle and the image classifier fetch. So we monitored the source for a total of 193 hours starting from April 2020 to September last year, and we detected a total of 46 repeat bursts in those observations. And this plot shows a timeline of our follow-up observations and burst detections. The error bar represents the spectral occupancy of the bursts. In all the bursts, we found no emission above 1.8 gigahertz, and all the bursts are quite band limited. In almost 70% of bursts, we do not detect any polarization, and most of the bursts are at low frequencies. So here is a gallery of some of the prominent repeat bursts from this source in our sample, and this is the dynamic spectrum of the pulse profiles, and it shows like the diverse pulse morphology of the burst. So we have quite narrow bursts with temporal profiles, temporal widths in microseconds. Then we have bursts with multiple components. Then we have comparatively broadband bursts, and then we have the usual band-limited repeat bursts. So the temporal width of the burst in our sample ranges, or most of the bursts range from 2 to 10 milliseconds, which is consistent with other repeating FRBs. However, there are 2 exceptionally narrow bursts in our sample with a temporal width of 100 on the scale of 100 microseconds. So here is a distribution of the fluence width distribution of the fast detected burst, and for reference, I have also plotted the fast detected bursts to compare with. We also calculate the cumulative distribution function of the burst rate, and we model it with a broken power law, and we found that we were sensitive up to 2 Jansky millisecond based on preliminary evidence. Moving on to spectral properties of these bursts, so the average emission frequency, we found it to be around 1.1 gigahertz, and the average spectral occupancy of these bursts is just 220 megahertz, which is 7% of the UWL bandwidth, and the bursts have a wide range of the spectral extent, ranging, so the delta nu by nu ranges from 0.05 to 0.82. So most of the bursts are narrowband, although there were few bursts which were outlier in this distribution, and which suggests a comparatively broadband emission. Their spectral extent ranges from 700 megahertz to 1 gigahertz. And interestingly, all these 3 bursts were detected on a single day. So we also observed, we also find subpulse drifting in some of the bursts, and we calculate the drift rate based on the standard 2D autocorrelation method. We find that the magnitude of the drift rate increases with frequency, and which we find consistent with other repeaters, and we also find that a power law fit and the index obtained from that is also consistent with the similar fit of similar analysis done for other repeaters, which suggests a common origin for such phenomena. Around 30% of the bursts in our sample are polarized, and we obtained an average rotation measure of minus 82 radian per meter square, which is completely different from what fast detected bursts had of around 542 radian per meter square. So clearly the rotation measure has changed. We find no evidence of circular polarization or any significant variation in the polarization angle in our sample. The degree of linear polarization has also a wide range, ranging from 0.3 to 0.8. We find that the degree of linear polarization decreases with frequency, and the depolarization sigma Rn, which is due to the Rn scattering. We find it to be consistent with what had been reported for the fast detected bursts. So we find clear evidence that the DM and the Faraday Rn is changing with time, and this is a timeline of the DM and Rn measurements in the follow-up that we did with parts. So DM is clearly decreasing with time, and the rate that we obtained is around -3% per centimeter cube. Yeah, thank you. And so the rate is -3% per centimeter cube per year. The Rm is also, we find it to be increasing, and for reference, I have also plotted the fast detected DMs and RMs. So Rm has clearly changed sign, and there is a potential of changing sign again in the upcoming few months. So more contrasting features are like emerging in repeating FRBs, and here I would like to highlight one such example from our sample. So these are two bursts, B15 and B16, which were detected within an hour, and these are dynamic spectrum of both pulses, and this shows how these two pulses are distinct from each other. So B15 is like a regular pulse from a repeating FRB. It has no polarization, it is around 18 millisecond wide, and it has multiple drifting components. Whereas the next burst is in a different spectral regime. It is unusually narrow. It is just 90 microsecond wide, and it is 80% linearly polarized. So this example shows how the burst from repeating sources are distinct from each other. Could be, and it also suggests the potential biases that is introduced while we are estimating rates and the pulse morphology of repeating FRBs. So this source indicates multiple RM sign reversals. If we consider the original path sign to be true, which suggests change in magnetic field orientation along the line of sight. We find that DM decreases with time, which is in contrast with other repeating sources, and the rate which it decreases is also more significant than the other. Yeah, sure.
Well, please go ahead and quickly wrap up your talk 6.
Yeah, sure. So such coordinated DM RM evolution could be due to expanding supernova remnant or an ejecta from compact bandwidth mergers, and that has not been observed before. And this source could be a link between the extremes and the mainstream population of repeating FRBs. And so this is my last slide here. I just show the phase space of repeating FRBs, and some of the potential questions that we should probe with distribution at microsecond scales. The FRB shows preferred emission frequencies, and the PA variation and circular polarizations are essential features but not prevalent, and the Faraday iron variation is a common theme emerging in repeating FRBs. So yeah, I will stop here.
Great, thank you so much. Any question from on-site?
Thank you, Pravir, for nice talk. My question is, how does your result compare with most prolific repeating FRB, FRB 121102? I remember that repeating FRB also show some decrease in the dispersion measure. I don't remember the rate, but also there's a huge decrease in the rotation measure. So how do you compare your result with theirs?
Yes, so 121102 also shows decrease in rotation measure, but that is quite extreme. The RM value is quite extreme, it's around 10 to the power 5. We don't have such extreme RM value, we don't have such extreme RM variation. Yes, in our source. Although the DM variation in 121102 was so the DM of the 121102 was found to be increasing and not decreasing, that's what we see in this source. So that is a distinction between them.
I see. Also, kind of depends on the theory, but maybe super remnant scenario also are maybe have explanation for this kind of case. DM decrease, but rotation measure could increase depending on the parameter and the time after the explosion. So thank you for nice talk.
Yeah.
Okay, great. We can keep more discussion later in the discussion section. So let's thank Pravir again. And I believe the next speaker is on site. Yes. So is